All right, so I thought I would talk to you about some work that my group has been doing, and it's actually work over time, but that people have been doing related to sensing and interconnect technologies. And it turns out that we end up doing a lot of this mostly motivated by communications problems, but then now being translated into other spaces like ecology and nanomedicine. So that was really important to me to find a way. I like working with things for things, but I really wanted to do things for people. So the last two topics give me something to work with, things for people. So I thought I would just start with a quote from my mom. We are the sum of our experiences. And I heard that a lot as a kid. And so I was told that this is a mixed audience of students and faculty, so I thought I'd give you a little brief overview of sort of my journey. I grew up in Houston, Texas, and so as you can see, I started at Texas A&M for my undergrad, and I was actually really inspired by NASA, which is in Houston, and a lot of the pictures for space exploration. And then when I was doing my internships, trying to learn about what is engineering, because I thought I would like it, but I didn't actually know what it was. I did a lot of internships in energy, which then pointed me in the direction of a program called the GEM Fellowship Program, which supported underrepresented students to get master's degrees. And that came with a partnership with an organization, a company. And for me, that company was Lawrence Livermore National Laboratory. That is actually where I learned about the concept of research. Prior to that, I had no idea what that was either. And it was through my work there that I was introduced to RF and microwave applications, because I was actually really interested in power electronics. And I had a problem in the lab because everything was so big, and the techs had to carry everything, and then they would make fun of me, and I was like, this is not gonna work. And the chief engineer said, why don't you go up in frequency? Then you can do everything yourself. And I said, perfect, I'm gonna go up in frequency. It was at Livermore also that I was introduced to institutions that would have programs in graduate school for RF, and Michigan's name came up. I did a triage of different faculty, and then ended up working with Linda Katehi as the person that I would do these RF applications that I could do by myself for graduate school. That led to me really developing, during my graduate school time, an interest and an understanding of packaging and integration at the microwave and millimeter wave regime. And it was primarily for space applications, which actually came on the back end. I wish I could tell you I had it all figured out and I just knew I wanted to do RF, but that's not how it went. It was very evolutionary, and I used each of the experiences that I had to kind of inform the decisions for the next one. From there, I graduated and started looking at how do I take the knowledge I had in grad school and apply it to other things. It was occurring around the same time that the wireless technology was just starting to take off. When I took my first faculty position at the University of Illinois at Chicago, I was then eventually recruited to University of Minnesota, which is where I've been since '98. And the work I'm going to talk to you about, really for my group, can be summarized by that pie chart. We do some sensor work, we do some integration and packaging, and because I was doing things with micromachining and silicon, I learned a lot about characterizing materials, and I'm actually able to use a lot of those techniques today for the people and thing work that we talk about. So I have these topics on the right: communication systems, looking at ways to think about environmental sustainability, and then in the biospace, really looking at diagnostic tools as well as how do we help advance transplantation. And we're just starting to look a little bit into security methods. In that time, what I'd like to point out is from '98 up until now, you'll see that these are the four things. There are many things, but these are the four big things that have been going on that have really sort of influenced and informed my decision. So as my mother would say, we are the sum of our experiences, and I'm going to share with you what my students have allowed me to contribute to in this space. So the first part is 3 parts. The first part is going to talk about sensing, interconnects, and materials. And then the next part, which I consider a team effort, the next would be my contributions to educating the next generation. I'll talk about my belief about the roles of professional societies, and then how we can think about broadening participation and mentoring. And then lastly, I'll end with what I think is important and sort of the undergirth of how one can have a reasonable career, and that is to have an important role of your support system, that's your family, as well as your professional. So let's start here. This is a picture that really got me excited, and it's a picture about communications for the future. This picture is probably about 5 years old now, 5 or 6 years old. But what's important about it is when I was here at Michigan, we were really looking at that top. We were trying to figure out how to make things really small so that the weight to deploy a satellite would be less, because fuel cost was the biggest cost for deployment. So I really kind of started out at the top. But what has happened since then is we always knew that everything was about the top talking to the bottom, meaning the terrestrial things, the communication systems on the ground. But over the course of 2 decades or so, we now have these autonomous vehicles, these drones that are running in the middle, and they are really giving us the opportunity to reimagine how communication systems might work. In the past, especially in the US, we had a huge and strong infrastructure for terrestrial, and we had satellites that we were using for specific applications, but now we have this new space that could literally allow us to think about reconfigurable communication systems where the drones could act as an intermediary face to move things from different places. That kind of occurs on Earth when we're doing our communication with each other because we're mobile, but this is just a different idea. What was important about that is when you start talking about big things, talking to little things, we really need to think about high directivity. We're talking about small things, which means we're talking about low power. And the systems that you put on things like drones need to be really small and lightweight. Otherwise, they won't be able to sustain themselves. So we started looking at antenna in a package concepts. And for that idea in general, people have been working on that. There's a lot of work here. Kamal's group does a lot of work in this space. Looking at PCBs and thinking about 3D antennas, there are 3 elements that you're looking for: high isolation, high gain, and if you can, good aperture efficiency. So these are 3 examples of applications that people have done in literature. And what you'll see from your left to right, what you'll see is that it's not that we can't make high directive structures, but because of multiple layers, they can get complicated. And when they get complicated, the wires that we need to connect everything can lead to a lot of loss, and they can also inhibit the kind of gain you can receive because you're sending energy through this in order to radiate. In the second case, if we can add polarization, it gives us a lot of flexibility in the types of communication systems. So in the second case, we can develop systems that can give you that dual polarization that occurs by the structure that's on the green layer. But again, when you start to have multiple antennas, that's a lot of different feed lines, and we're worried about loss oftentimes, and especially if you go into higher frequencies. So you would really like to have the ability to create flexible antenna designs with different polarizations, but you'd like to keep the feed line structure simple if possible. The last one is, I've got this dual polarized system. I'm printing it on a ceramic material called low temperature co-fire ceramic. And in this case, my problem is at the surface where I release energy to make the beam, I need to think about the efficiency. Even if I have a good system inside of all of the layers, when I get to that last level, what I like to know is if I put a unit in and I take into consideration the losses to get it to the surface, I want to be able to release most of it, and that's going to be what aperture efficiency does. So I have a student who did a really fantastic job of looking at different techniques for that. One of them is a technique that says if I have one antenna element versus a 2x2 slot array, how does the performance look? And the second is that he said, well, I think we can get away with using one antenna element if we could replace the 2x2 with a frequency selective surface, or what we call a partially reflective metasurface. So I'll just kind of give you the highlights for that. So what Aditya did in the first design on the left is he created a multi-layer structure shown here that basically has 4 antennas. This is the 2x2 that's being fed inside by some interconnects from a source. And if you take a look at something like that, what we could say is that, okay, the stacks are minimized, about 5. It's a little bit more complicated of a design in terms of the feed lines. And in this case, we also need to think about how do we best do the antennas. He contrasts that to the second case, which is this metasurface one that I talked about. And we can use this metasurface, which is going to sit at the very top in the same location that these would sit in that example. And in that case, we can get a really simple, use a simple reflective surface to get the shape of the beam. We can also think about the pre-manufacturing process for that, but the trade-off is I may have to utilize more layers to get the proper performance. So I want to give you that. Now this is a busy slide, so I'm going to narrate you through it. The first one is that over here, you can see the structure. 1, 2, 3, 4. So this is a 2x2 array, about 6.6 millimeters squared, and these are the stacks. And what we have is we start by feeding here. This splits the signal into 4 parts, and these signals then radiate up to those antennas. And what they ultimately do, if you look at the top view, is that they look something like this. Each one of the rectangles releases energy, and that energy combines in the far field to give us a really narrow beam that's very high gain. And then these are just examples of what they look like at the different layers. If we proceed to think about what does that mean, there are a couple of things we discovered. One is if each antenna has its own cavity, we can make that cavity with these vias. We found that the size of that cavity could dictate the range that we could have good radiation in. So this plot, which is very busy, really tells us 2 things. If you pay attention, if I can get your attention to the pink curve, which is shown here, you'll see that the pink curve has 3 dips or resonances. That's undesirable. And what we discovered is if you shrink it, and you shrink it as a square, that's the black curve, you'll notice that it becomes flat. This is the ideal space. So what it means is even though physically I need to have this large rectangular space around the antenna, I can bring the cavity walls closer and I can optimize the performance of that. So that's the first part. The second part is when I have arrays, it would be like, let's say, the 4 of you talking. And if you're all talking together, and I'm trying to organize that, it's very difficult to get coherence if everybody's coupled to each other. So what we'd like to be able to do is let you talk, but we don't want Professor Terry to hear Professor Sarabandi, or for Professor Sarabandi to hear Professor Winful. That's not good. So what we found is by utilizing this idea here, we can compare the performance of a 2x2 array with and without those small windows that I just showed you. And what that does is, and the only thing that's important about this, is that when we look at the fence around the individual elements, without that, so we just use the 6x6 and just one big cavity, we see these dashed lines, which is talking. Anything close to 0 means they're talking to each other. When we introduce those small fences around each element, all of a sudden in the regime of interest, we get silence or more silence. And so the dip is good because that means we've reduced the communication between individual elements, which is important for the performance of the array. So the next one is then to say, okay, now that I know this, now that I know this, let's think about building that array, the one element source with the metasurface. So this is the second design. This bottom part looks very similar to what we had before, and then that 2x2 would be placed here. We replaced that. We only have one antenna in here, and we replaced that with the stack and this metasurface. So that's this guy. If we take a look at what that implicates, in the near field, we can look at 2 things. We can look at the reactive near field and the radiating near field, which is in the black. What that really means is, what does it look like on the surface, and what does it look like just slightly above the surface? Starting from left to right, what we find is when we have the 2x2 and the large cavity, you can see these peaks, which suggest that that's a little bit of the conversations, the max. But you see there's a whole lot of overlap, which tells us that they're interacting with each other. And that means that when I look in the radiating field, while it does come back together, I don't have a very strong signal. If I introduce the individual cavities to isolate, Now I've got very strong peaks, which means now all of that energy is staying focused. And when that combines, we get this nice beam, which means that the signal is peaking in the center as it should, and that's more of a Gaussian. What we were able to determine is that I can do this, or I can have one antenna and just put this metasurface on top. It immediately in the reactive field combines everything, and then in the radiating field, I just get a stronger signal. So this is a lot simpler design to get very similar performance to the 2x2. So this would suggest that if you have a lens, where the lens would be like my glasses, and I have a source behind it, I can control what the signal looks like if I just come up with the proper lens design. And then finally, this one says, if I now compare everything to a benchmark, where the benchmark is just a normal 2x2 array with not much else processing, what you'll see here is with a single element and no reflective surface, you're going to be down here where the green level is in terms of gain. A 2x2 array basically focuses things so that you get more gain. And what this shows is that, yes, I can get better response if I'm able to include the fence, but it also shows that if I do the one element design, I can get comparable performance, and I get that 6 dB back recovered from my system. And that's actually excellent, because what I'm doing is able to accomplish that by not having to deal with loss as much from the interconnects, because there are no interconnects. And then finally, when we look at gain, whether it's realized or regular gain, what this allows me to see is that different layers I can use different layers to control what the peak is. By changing the height of the layers, I can actually use that to tune or move the signal around, which means if I had a mechanism for making those adjustments, I have a tunable system. So we realized that this was for 60 gigahertz, and we ended up doing a scale model and the realization for that. That's what it looked like. And what we were able to show is that from the theory, we can see that the gain, which is going to be comparing the green, which is the antenna without a surface, to the other two designs that I've talked about, the red and the black, you can see that around 12, both of them give you the higher value of gain compared to the green curve. The other thing is that if we think about efficiency, we can see that when we compare that to other work in the literature, we're actually able to see that our responses are quite comparable. In fact, we get higher aperture efficiencies here and here compared to what's already available. So the conclusion is that you can either use a lens, a metasurface, to focus the beam, and that you don't need a complicated lens to accomplish this. You just need a reasonable pattern that can be replicated. The other thing is that in order to manage loss, the losses are ultimately what consumes the power gain, and you can reduce that by eliminating the extra feed lines. We showed that by isolating the elements, you can compensate for some of the loss, because that loss is really the two elements talking to each other. So that's another way to do it, but that's a more complicated structure to build. All right, so I'm going to shift gears and talk about interconnects, and this is work that was done by my student Yali. You saw in the beginning that I talked about technologies that were informing or influencing the work. You know, nanotechnology really started to get a lot of interest, like AI, when I actually started working in the late 90s. So this is a project that took a few decades actually to get to, because I have a colleague who works on nanowires, and we've been trying to find a way to work together for years. But her technology is pretty mature, and so is our work, and we were able to combine those to show the consequence here. What we're interested in doing is trying to figure out, can we reduce loss in the sub-millimeter wave regime by looking at interconnects based on nanowires and vias based on nanowires. So the idea is basically to think about the via not just as a uniform post of metal between two surfaces, but can we make small wires in parallel and leverage parallelization benefits to reduce our inductance and our resistance for signals going from the top surface to the bottom. At RF, what we normally worry about is the skin depth, both in this direction, if this is the top of the wire, if it's a whole wire system. Here we have wires distributed everywhere, and we have current when it comes across that is then pushed through each of the small wires to the other side. These nanowires have very smooth sidewalls, so their resistance with copper is really small and comparable to the theoretical limit. So for this, because these are really, really tiny signals, we cascaded a number of those structures together so we could get enough signal to measure loss. And what one of these looks like, so this one section would represent what's happening here. We run a signal up through the top of a coplanar waveguide, through the nanowires, underneath this region that would house nanowires, back up through this electrode, and we do this over and over until we get to about 5. And we just did a simple study to say, what role does the width of the ground plane play in our assessment of loss, and how can we anticipate what that might look like? So dimensionally, we're talking about things on the order of microns in their width dimension, which is shown here. We looked at 2 designs, A and B. The primary difference between A and B is that if I want to run up to several hundred gigahertz, I need my aspect ratio of my cross-section to be smaller. So I'm showing you one that's for less than 60 gigahertz and another that's for less than 167. We were interested in going up to 300, but we have a problem in the thickness of the substrate that was not resolved when we did this work. So you'll see where that impacts things. But in general, we're really just trying to figure out if we have a via, this is fixed on both. If we have a via, does the placement matter? And does the width matter? And that's what I'm going to show you next. So nanowires can be grown in an anodized aluminum oxide, which my colleague makes. We basically take a silicon wafer and we deposit aluminum, and then we pattern and convert that aluminum to a porous medium. So these holes that you see are the porous media that occur. Because that's on top of the copper, then we electroplate the copper through those holes, and that looks something like this picture here. So at the top, you'll see those wires coming up through this dark material here. And then you'll see this region, which is the copper, that sits on top of silicon. So in order to make these structures and to look at the response, we've got to put taps on top of so that we can force the current to go in and through those structures. So when we compared our results to literature, the bottom 2 are our results, and the top 4 are different types of structures in the literature. The one that is closest to our work is number 3. It's also done on AAO, but on a commercial version of AAO. And what we find in terms of responses to compare against, their material is about 50 microns, whereas our material is really thin, but the trace is longer, so the distance is similar. So our thickness is about 1.2. And what we found is for the wider line, which is A, we're at about 0.0275 dB at 40 gigahertz in the via. And then for the trace B, which is the more narrow one, we see that the losses go up a bit, in part because we made a smaller trace. So we've got to deal with those additional losses there. But these both of these have been very promising for the notion of using nanowires, especially for multi-layer systems in integrated circuits. When we compare the response of that, on the left, where it says standard, is a standard coplanar waveguide. If you are not familiar with that, if we take a cross-section cut, the standard coplanar waveguide has a signal line in the middle and 2 ground planes on either side. And what we did in this work is we built the nanowires on top of the electrode, and we're measuring this thickness here. This is different from the via, because with the via, we take a signal across to push the current down to come under. With this one, what has been fascinating is that what we saw when we look at putting nanowires just on top of, at about the same height that we see for the copper itself, we see 2 things. The black is the standard, And this is a curve of loss. So what we find is loss is going to continue to go up and get higher and higher as you increase in frequency. But with the nanowires, what we're noticing is that we see a distinctive break where the losses are lower, and they're consistently lower. We didn't have a measurement. They were using modules, so we didn't have this band covered. But we see for this particular architecture that losses can actually be reduced by putting those nanowires on the top surface of that electrode. And this is an important observation because historically we've tried to get rid of loss and mainly control loss by the dielectric, but this tells me that I can also look at the conductor as a potential mechanism that I can control for loss as well. This is just the conclusion, is that for CPW, if the ground plane is narrow and you place the vias close to the slot, we get the best response. The thickness matters, so if you have to go really high in frequency, start with a thinner wafer. But that would be hard to tell a graduate student toward the end, I need you to go redo everything when they're trying to graduate. And then for the nanowires, what we're finding is that if we integrate the wires on the top surface, we can see that there's a promise for having lower loss and control of that going up to 180 gigahertz. So I'd like to just shift now. This work that I just presented to you, Something Moved, was done by my student Aditya, and also for the metamaterial stuff. And then this work that I just showed you for the nanowires was a team effort between myself and my colleague Beth Stadler and her group, and UT Dallas with Rhonda Henderson and her group. And those people, that was an SRC project, and the other was an NSF project. All right, so now I want to just shift to giving you just some glimpses of what we're doing with the biological work. We were interested in doing sensors, and this picture here is the first one that we worked on. This is some cancer cells from dogs, and we're interested in attaching nanowires, magnetic nanowires, to these as biolabels. And so what you'll see is where you see green, those are nanowires that have been taken out of the matrix that I talked about, and that particular material is cobalt. I'm going to talk a little bit about this. And then we are also looking at nanowires for a different type of identification system, looking at their ferromagnetic resonance. I won't talk much about that. And then for the Ecology project, we're looking at using sensors that are based on frequency selective surfaces to measure water content in real time for trees, young trees, the samplings, because my colleagues have an interest in understanding oak wilt. And this is a disease that runs through the root system, and then it propagates very quickly to damage surrounding trees. But it turns out in the Midwest, oak trees are about 40% of our forest population. So to have them be sick or die could have pretty devastating consequences on our ecology. And then lastly, we're using both commercial sensors and sensors like the frequency selective surface to measure cryoprotective agents, biological cryoprotective agents, which are basically antifreeze that's safe to put in biological systems so that they can be cooled to cryo temperatures. So let me just give you a quick experiment on this one. With this one, we basically made nanowires from that AAO. We use commercial materials there. The pore structure looks like this, and once you anodize them, they have about 12% porosity, and the holes are around 40 nanometers. We put that in solution, and we're able to grow nanowires up. And then once we grow them up, they look something like this. We release them. Once they're released, we're able to then put them into solution where they attach. They have coatings on them. They attach to the cells that are the anti of the coating. My group was basically responsible for characterizing the wires before they come out of the matrix. So we use magnetic DC fields for that, along with AC fields to look at response. So when you look at these two curves, they tell us in a different way whether or not a material is present. The top one is specifically for cobalt, and what we end up looking at is if I hit this material system on a circuit with a DC signal that can range anywhere from 0.4 to 0.6, we can see dips show up both in the positive and the negative. What we're looking for is what is the AC frequency response that the wires absorb when they're exposed to a particular value of DC. And so what this shows is that these wires for cobalt, when we switch from this value to the highest value, will absorb RF signals from 25 to 40 gigahertz. And that takes about 1.5 Tesla of magnetic field strength for us to see that. This technique is something we developed after the fact because that requires you to understand a lot of what you're doing. And we wanted to figure out, is there a way to determine if these different materials are present by just looking at phase data? So if you take the derivative of the phase data, it turns out that you can see these peaks by looking at the derivative of the transmitted signal, and it gives you an indication at these various points of what's present. Because we know what the response should look like from the Cattell equation, it's a linear line that tells you if you hit it with this DC field, you should see this AC field. I can tell you specifically which one of these is present. The amplitude is also an indication of the magnetization strength. So, for example, iron has a stronger magnetization than nickel, and nickel has a weaker magnetization than cobalt. So that was one of the ideas we had for developing biolabels. Our next step there is to really look at, okay, that's fine in matrix, but when they're out and laying on different cells, how will we measure that? And that's something we've been trying to explore more carefully. This is the one that has to do with the trees. So if you can see in this picture, there are a couple things that we're doing. We're using a resonator at the top. And what we found is that if you take trees that are, in their environment, and we attach these resonators to these trees, the current technique is to put a probe in the trunk when they're mature trees, and so that's invasive. And we were trying to see if you could study, in a laboratory setting, they study younger trees. You can take samples from this tree, and the method they use is destructive. They take the sample, they cut the sample, they dry the sample, they weigh the sample, they go back and cut more samples, they dry the sample, they weigh the sample, and then they go back and forth to predict what the moisture content is. Our technique just says if we put the sensor on here and we run the response over time, then we should be able to predict what the response looks like. So in this part that you're seeing here, we did a similar experiment where we took a sample, measured it with this amount of moisture, then we weighed it and compared it to theirs. So you'll see here that this basically shows that the techniques are comparable, and we have data where we've been able to show over the course of like several weeks how the water cycle, they call it the diurnal cycle, how that changes over time. In their case, they're trying to stress the trees, so they systematically withhold water to try to replicate what happens when we're in drought circumstances. That work is being used to empower this work, which is the crowd protective agent work that I won't talk about today.
Rhonda, quick time check. We've got the room for 10 more minutes. So
okay.
Just want to make sure you get that.
Yeah. So the last thing that I wanted to talk to you, last couple of things I want to talk to you about is really how active engagement is a fertilizer for career development, since I know many of you are graduate students. You're here, and I know when I was here, I was like, I just want to graduate, and I really didn't think about anything else. But I want to say to you that I'm sure if you are in anybody's professional, when you go to your conferences, that it's bigger than just the conference and the paper. It's the community that conference represents. So in your society, there are different things you can participate in. I highly encourage you to participate. Those people will become your network for your future. In my case, this is sort of a timeline of how my things happened. Once I became a professional, then you sort of start to get involved with being behind the scenes, judging papers, selecting papers and journals, and meeting people here. The networking piece can occur through some other activities that are going on that I also know are available for students. It's really a good idea to go do those things. Every time you go, you build your network even more. And so now I'm sort of over here where I'm doing a lot of different things, and sometimes those things can result in some acknowledgments and some nice acknowledgments, but The more important thing is to find your thing in the professional society and engage, because more than anything, you benefit from the network that you form. And I just want to highlight that we created a program that's a broadening participation program for NIMS called Project Connect, and that is actually with 3 Michigan alum, myself, Rhonda Henderson, and Tom Weller, all from the Rad Lab. And we have, to date, brought, this will be year 11 for us, about 160 or 70 students from various different underrepresented groups and women to our meeting. And we find that the vast majority of them have stayed in RF, and many of them have gone on to continue with graduate school. This starts with undergrad, juniors and seniors, and first-year graduate students. So you can also influence and add to the system that you are also benefiting from, which is an example of that. And then the last thing is, I just want to talk about family. So I just heard an article on NPR that said, people shouldn't think that the workplace is their family. They're not their family. And I was like, well, I don't know. I think differently. I think that, I think there are many different types of families, and I want to be in environments where I can find a few people that I wouldn't mind hanging around. So I will say to you that for me, the professional student family, this is Project Connect from 2019. This is me. There's Kazim, a Michigan graduate. There's Tom Weller. There's Scott Barker. I will tell you a good percentage of the people who work behind the scenes are Michigan graduates who support this project. Here's Rhonda. And that's been awesome to just see us come together many years later to work together on a cause that's super important to all of us. This is my group, great group of young men who crack me up all the time. And then this is my family. And I would like to just say, you're not what you do, but what you do reflects who you are. So this is my family, my mom and my daughter, and then this is my daughter's godmother, and this is Rhonda again, and a few other people you don't know. This man was a mentor of mine, Dr. Howard Adams. He's very famous, actually, as a mentor and a leader in the country, but he was over the GEM program. This is another group of my students, and of course, that's my family. So I just want to say, when I end, that what we do is informed by many things. We really are the sum of our experiences. But I hope that when I was a student, all I was thinking about was graduating, so I didn't think about any of these things. But I want to give you hope that there's a lot more. Oh, and this was my last day. This is me on the day that I defended. And this was my roommate when I was a graduate student here. So I'd like to end on that note.